Okay, welcome back to the wireless channel. This is the channel where we discuss papers about wireless communications. Today I'm going to discuss a paper that got recently accepted to the WCNC conference in Milan, and it's titled Tone Reservation Based PAPR Reduction Using Manifold Optimization for OFDM ISAC Systems. My name is Getuar, and you can see also my colleagues here. I would like to use this opportunity also to thank the colleagues from Continental that supported this work. With this, we jump straight into the presentation. Okay, this is the outline that I'm going to discuss today. First, I'm going to give you some background and motivation for my paper, and then we're going to discuss what the problem is, and then the solution, and at the end, I'm going to discuss the performance evaluation. So let's go straight to the point. Orthogonal frequency division multiplexing was used formerly in the fourth generation systems, also in the fifth generation systems, and is a cornerstone of modern wireless communication due to its robustness against fading and efficient spectrum utilization. This we know. Also, it is expected that OFDM will be used in the future sixth generation systems. Speaking of the future, the recent emerging ISAC systems, or integrated sensing and communication, combines communication and sensing waveforms into one dual-purpose waveform. So the motivation of this paper started from the question how to design waveforms that are suitable for both communication and sensing, but also efficient in terms of power consumption. So with this question in mind, we start explaining our problem and solution. So we started by saying that OFDM is such a great invention and has many advantages, but it also has disadvantages. And one of the biggest drawbacks of OFDM is the so-called peak to average power ratio, or PAPR. Because OFDM is based on the Fourier transform, and you have many subcarriers that are added during this linear transformation, as seen in equation 1. Now, due to this superposition of multiple subcarriers, OFDM signal can exhibit high PAPR, which is defined as in equation 2 as the ratio of the peak power to the average power. Even though this is not very common, it can happen, and it's very bad for power amplifiers, which will create some nonlinear distortion, or power efficiency. For example, if you think of some receiver design, you have some high power amplifier and it has a certain range that can accept signals. However, if you have high PAPR, this amplifier will cut the peaks, which will create some distortion of the signal, which we don't want. With that in mind, now naturally we ask ourselves, how do we solve this issue of high PAPR? And during the past 2 decades, researchers have developed many schemes for PAPR reduction. Among these schemes, one stands out for its simplicity and efficiency, and this is called a tone reservation, introduced more than 25 years ago by Cioffi. And it was originally introduced for OFDM systems, but can be used also for other waveforms. In here, a set of subcarriers are reserved to balance the OFDM signal, which means that it will reduce the peak and make it it will make this PAPR level down to the peak, as it can be seen in the illustration in the figure 1. So in the left, you have the time domain functions. So you have some data signal, which as it can be seen in blue, it has a high peak, and then you will have some reserved tones in red, which when added to this data symbols will create a new signal X, which as it can be seen now has a reduced peak and consequently a reduced peak to power peak to average power ratio. It's worth of mentioning that these reserve tones are mutually exclusive to data, so that their intersection is empty, so that we don't have any conflicts with data and these reserve tones. Of course, as it can be seen in equation 3, these reserve tones can be expressed in time domain or frequency domain, since the Fourier transform is linear transform. Now, as I said, this work has been proposed by Trophy and his PhD student from Stanford University. They originally formulated this problem as a convex problem, or as it is known as a quadratically constrained quadratic program, or QCQP, expressed in equation 4. Here we see that you have the data symbols, and then in time domain, and then you have the reserve tones in frequency domain transformed by the inverse Fourier matrix, constrained to some power budget. So these reserve tones have to obey some power budget. It has to be mentioned that this R vector is a sparse vector, which means that it has some dummy data that are going to be used for peak reduction, and other are zero, because we want to transmit also data. Otherwise, this system would be inefficient. It is worth of mentioning also that this problem 4 could be projected into some linear programming and then can be efficiently solved using some CVX toolbox or interior point methods, which are known in the optimization community. Now, I'm going to discuss about the sensing and the waveform design inspired by the emerging of ISAC. So in integrated sensing and communication, we want dual purpose waveforms for both communication and sensing. But here we have some challenges. First of all, the question remains how to design waveforms that are suitable for both communication and sensing. Now, to answer these questions, there are two schools of thoughts. First, from sensing community, you can have a sensing-centric waveform, which can be used for communication. The other one can be communication-centric waveform, which can be used for sensing. We will focus more on the latter than the former, so we will naturally ask the question, now, which communication-centric waveform is suitable for sensing? And this question was answered recently, very recent, by the fellow researchers. Funny enough, this title answers directly our question above. So OFDM achieves the lowest ranging side lobe under random ISAC signaling, which means that OFDM, which is a communication-centric waveform, achieves the best performance for ranging or sensing. And we're going to discuss about this. Now, usually from the communication perspective, we always measure our performance using some performance metric, usually sum rate or signal to noise ratio. In sensing community, however, the autocorrelation function, coined as ACF, is an important performance indicator. The aperiodic autocorrelation function can be expressed as equation 5, nicely in matrix form. In the other hand, the integrated side lobe level of this autocorrelation is also another key metric for range estimation in radar systems, which is expressed as equation 7. Notice here that index 0 is skipped, and this is the whole point of the side lobe level, because for K0, essentially there is no delay, which means that for R0 we have the variance or the power of the signal. So what we want in radar waveforms is to have minimal ICL or zero ICL, which means that we will have some autocorrelation function with one peak at 0 and everything else should be as low as possible. Now, theoretically, this ICL can be 0, but in practice, it's close to it. Now that we defined OFDM, PAPR, and how to design good sensing waveforms, we present our problem and solution. As you saw from the PAPR reduction section, uh, you might think naturally that these reserved tones transmit only dummy data to reduce the peaks. But this is quite inefficient because we're sending these reserved tones and we're not transmitting anything. However, from the communication point of view, it is not possible because we cannot design at the same time some reserved tones that will cancel peaks and transmit data, because then data will be distorted. What we can do here is to use these reserved tones for sensing, and this can be possible. However, from the discussion of ICL and autocorrelation, we understood that for minimal ICL, we should have unimodular reserved tones or unimodular symbols. Only then, and there is proofs for this, we can have minimal side lobe level. Now, inspired by this, we can formulate a new tone reservation problem as seen in equation 8. So we have the same objective, but now the power budget is not there as it is constrained by the unimodularity of reserved tones. However, I mentioned that the previous problem was solved using some interior point method from the convex optimization toolbox. However, now this problem becomes non-convex due to this unimodularity constraint. And now we cannot apply those methods. Here it comes the optimization, the manifold optimization framework. Recently, manifold optimization has caught attention of researchers, especially for problems that are constrained to orthogonal matrices, fixed rank matrices, or unit norm matrices, uh, or simply put, any set that can be expressed as a manifold, which is a space that locally resembles Euclidean space, but globally might be very complicated. Now, our problem can be reformulated as an unconstrained optimization on a manifold. We choose manifold M to be the set of vectors with unit magnitude or vectors that lie on the complex unit sphere. With this, we can formulate the new problem as an unconstrained optimization problem as seen in 9, which can be efficiently solved using the manopt toolbox, which supports both MATLAB, Julia, and Python. However, because these toolboxes use some numerical solvers, it might be slow. And to make it computationally efficient, we propose an algorithm a low complexity algorithm by finding a closed form for the partial derivatives and the projection used. As it can be seen, the partial derivatives are solved as in equation 11, and then the projection used is showed in equation 12. With these equations, now we can go ahead and construct our own algorithm, which is coined as the projected gradient descent for manifold optimization, and follows like this. So we give this step size. P is the norm that we're using, of course, because as it can be seen in equation 10, we cannot use P infinity, as this would be then not differentiable. So we use an approximation. But I will explain later that this P, if it's high enough, then it works sufficiently good. Then we have the data signal and the Fourier matrix. First of all, we initialize R with random phases on the unit circle, and then after we compute the gradient shown in equation 10, we update the reserved tones by the gradient descent step, and then we project this vector to the unit circle until convergence. And then at the end, we have the optimal reserved tones R. With this, now we go to the performance evaluation. The first plot discusses the convergence of the algorithm 1. As it can be seen in the title, we use the OFDM system with 512 subcarriers, where 64 of those are reserved for reserved tones for PAPR reduction. And we used 16 PSK modulation. As it can be seen in the legend, we use different P's for the P-norm approximation, but as it can be seen there, as long as P is in the range of hundreds, then even 50, it doesn't matter if you go higher. It's sufficiently if you choose P 100, and then you reach almost as good as P would be at infinity. Of course, here the reserved tones were chosen. You can choose the reserved tones to be randomly allocated or via some scheme. In this case, I choose them to be every 8th subcarrier is a reserved tone. So it would be 1, 8, 16 until 512. Here we present the PAPR reduction performance. So the black line is the original PAPR of OFDM, which is quite high. And then the intercepted line is the optimal tone reservation technique that we presented earlier. And then the black ball present our proposed method with P50. As it can be seen, we lose very small performance. It's maybe half dB. But we will see later that we have a huge gain in sensing performance. So this algorithm somehow gives us a trade-off between PAPR performance and sensing. And for that, we discuss in the next slide. Here, as I stated earlier, we use the aperiodic autocorrelation function. And as it can be seen here, I plot the normalized side lobe level in dB. And as it can be seen, the proposed design tones that are in red are almost 90% same as the OFDM 16 PSK, which by the way was shown by other researchers that is the optimal waveform for sensing. So even though we lose slight performance in PAPR reduction, we have the best performance in sensing in radar terms. Also, it's worth of mentioning that if you would have used the optimal tone reserve, the peak reserve tones that you would get from the convex problem, the line in pink, the performance is very bad, and this can be illustrated via some ranging experiments that I'm going to show also later. But the important point here is that we want very low side lobe levels, because if you have targets that are very close to each other, then you will have the so-called masking effect, or you are unsure if your side lobe is another target or it's just your poorly designed waveform. So you don't want that. And for the last plot, we have a range estimation experiment where we used the proposed designed tones, the optimal reserved tones from the convex problem, and the OFDM 16 PSK symbols. As it can be seen in our ranging experiment, where we used 64 reserved tones, the performance of the proposed design tones is the same as the optimal 16 PSK symbols. And as I mentioned, this was shown, it was proved that this is the best you can get from OFDM. And if you would have used the optimal reserved tones, then the range estimation performance will not have been that good, and we have a huge gain in terms of RMSE, which is in meters, by the way. Now with this, we have shown that even though we lost maybe half a dB in PAPR performance. We have a huge gain both in terms of range estimation and autocorrelation uh, uh, properties, which are both very good indicators of sensing performance. Now, to conclude this, I would like to again emphasize that we propose a tone reserve based PAPR reduction method for OFDM ISAC systems where the reserve tones now are not used just for dummy data but also for sensing. This sensing is done by these unimodular reserve tones, which were designed via the Manifold optimization framework. Again, this scheme achieves near optimal PAPR reduction and very effective sensing with low complexity. Now in future work, we will try to extend this to bistatic radar and also maybe optimize the location of these reserve tones. As I mentioned, until now, we are doing it randomly or predefined. With this, I conclude my presentation. Thank you for your attention. And if the audience has some questions, I will be happy to answer.
Thank you, Getwar. Very nice work, very clearly explained. Thank you very much. I have a couple of questions.
Yeah.
First, just for my understanding, because you moved away from the slides too fast before I could observe that. But I assume that when you're comparing all your comparisons against the 16 PSK OFDM, your scheme is using a 16 QAM. Is that the case? Here, for example, the QCP
No, no.
QCQP, no? So what's the
This,
modulation they use for the other systems compared against 16 PSK?
First of all, if you would have used OFDM 16 QAM, which I
No, no,
didn't
no,
show
no.
you.
No. That's clear. This one, I know it's 16 PSK because you need to have a
Yeah.
norm one for the sims. For the other sim, for the other ones, are you using 16 QAM or what?
No, so these black balls are
Yeah.
literally the design symbols that I got for PAPR reduction, and I use those symbols for sensing. Here, there is no modulation, so I'm not using any PSK or QAM. This is not
So you are okay. So you are only evaluating
yes,
the here in this figure the sensing performance.
yes,
So
only
okay,
this.
the root of my question is the following: that of course, if you're using OFDM 16 PSK, you are sacrificing bit error rate in favor of having the optimum sensing performance, right? Because you are forcing your system to work with a modulation that is quite crowded, and everybody knows that for sufficiently for a range of SNRs, would be better to use 16.1.
Yes,
Now, your scheme and enables PAPR reduced OFDM using a 16 QAM, that's how I understand, thanks to the carefully designed tone reservation tones, which only the tone reservation tones have a PSK. They are
yes.
uh,
This is
correct.
true because if this
So that's
data
the root
D,
of my question.
yeah, this data D can be
Mhm.
now QAM. It doesn't have to be PSK. There
In
is
your
a
system.
yes in my
But
system.
you are comparing only that's okay. Then my
Yeah,
question becomes a suggestion. You need to, I think it would be a good idea to compare the bit array advantages
yeah.
of
Well,
using that, right? Because essentially, yeah, because
of course. If I use 16 QAM, as you said, 16 PSK has little Euclidean difference between symbols, so my BR would be better
for sure your
for
system,
sure.
based on all the results I see, since you achieve essentially the same PAPR, very close, yeah, to the
Yes,
PAPR of 16 QAM and the same sensing performance. You sacrifice nothing and you get gain. So it makes sense for you to evaluate the beta rate. That's what I'm saying, and perhaps even consider alternative metrics that measure all of these things together, right? Because if you think about that, you could, in principle, lower the transmit power to achieve the same rate and therefore have an even lower demand on your power amplifier, the transmitter, without sacrificing anything else. So I think my question became a comment.
Suggestion.
But
Okay.
yeah, but then I have another question, which is now if you go back to the formulation of the optimization problem, yeah, go forwards. I think from here. Yeah, okay. Well, in the paper, I believe you had an intermediate one where you also had a power constraint, but that was one of the questions in the power constraint.
Yes.
In the
So because you're limiting now the reserve tones to be unimodular, then the power constraint is governed implicitly by this constraint, right? You have
right.
the
That
norm will
that's
be, yeah. So that's why
clear, clear.
I omit it, yeah. But
Yeah,
here
it
the comparison is fair. I also limited this to the same power, so we're,
okay, so that was going to be my question actually.
yes,
That
yes, yeah. Power,
under your scheme, because you're doing the optimization over the manifold, you no longer need a power constraint. But for
yes,
the other schemes, you need to have that power constraint. And my
true.
question was that if this comparison here are done under the same power for all the schemes, and you
Yeah,
answered the
that
question.
is true.
But okay, but now I have a follow-up question, which also might be in the end a suggestion, which is if you go to the ambiguity function, yeah. So now you see, look at what's going on in your manifold optimization scheme. You get a side lobe behavior that, in a sense, even better than the OFDM 16
Yeah,
because you go below that. But we know that going below the black line is useless, right? Because that the highest point is what defines the peak to side lobe ratio anyway. So it seems to me like there is still a room for improvement in the sense that, okay, imagine that this red line that you had here was not going down towards the zero, but actually stays flat, yeah, in that range. The reason for asking this is the following. What if you were to relax a little bit the constraint of norm one on R, right, on your tones, in favor of even better performance in terms of communications? So if you go back to your optimization problem again, what if you allowed a little epsilon, right? So the R uh, would be less or equal to one, but less or equal than one, but larger or equal than one minus epsilon. So you keep it inside a certain band and you control the band. One can even think about optimizing the band such that some objective is reached. Have you thought about it? Do you think this
okay, okay.
makes any
So
sense?
you think of designing these reserve tones on a donut, essentially.
Pretty much, yes. Very good.
Yes.
Yeah. Over a
Okay.
donut.
Then yeah. So in that case, maybe there is another trade-off. So we might get even better PAPR performance because now the solution space is
Exactly.
much bigger, and
Yeah.
just a little deterioration in the
In the sense.
autocorrelation function. But
Yes.
yeah, as you said, maybe that's
Which
not
is
a big
not
deal.
significant.
It's not a
Mhm.
big deal. Yes. This
Yeah.
this distance is only of academic interest. In practice, you would not notice it.
Exactly. Precisely. That's my point. Of course, the problem would be harder now, I guess,
Yes.
because you'd have to optimize over these these which is not even a manifold. I don't know if you can call that still a manifold, but it's a donut.
Yeah.
Yeah, that was my suggestion. Okay. Thank you very much. I don't have any further.
Okay. Then I'll
Brian?
guess.
No questions here.
Okay. Then I guess that's it for today. Thank you for watching us. See you next time.
Thank you.
Thanks. Bye bye.